Welcome to this video on ISP Task 2 on Astrophysics, which is part of Unit 5 of Edexcel Physics. That's the A2 unit. This video is going to be on parallax and standard candles, Hubbles Law, the age of the universe, and Doppler shifts. So pretty straightforward standard tasks. Let's get straight into the explaining everything tasks, and then we can get on to some questions after that. So, describe two methods on finding, or should be of finding, the distance of stars. Include diagrams, okay? So the two main methods that we talk about are the parallax method and also using Hubbles Law. Remember, parallax method only works for nearby stars when compared against a distant background, because the way the parallax method works is by essentially plotting the position of a nearby star compared to a faraway star. So if you want a diagram for that, parallax distance to stars. Yep, so let's find one that has a bit of trigonometry, yeah, here we go, this is a good one now. So you can see that during the rotation around the Sun, if we were to look at a star, a nearby star 6 months apart, we would see it against a different background of stars. And from that we can measure an angle, and by knowing one distance, we can use trigonometry to figure out the distance between us and the nearby star. Okay, or the distance between the Sun and the nearby star. So whichever side you want to figure out of that triangle, you could. Remember, it needs to be a nearby star, otherwise the angle is too small to measure. Okay, if it's a nearby star, the angle is large enough. We're still talking about a few degrees, not particularly a large angle, but it allows us to measure the distance of stars quite easily. So that's one of them. Hubbles Law, okay, just to quote that over here, which is V is equal to H naught, which is Hubble's constant, D. Okay, that allows us to also figure out the distance of stars. This allows that to occur by the fact that by knowing how fast it's going, we can figure out how far away it is due to the value of Hubble's constant. Well, what's going to allow us to figure out how fast they're actually travelling? Okay, well, the speed we can actually figure out by using the idea of the redshift, because the idea of the redshift allows us to figure out the speed of a galaxy, speed of a star. Okay, so the way we do that, if I share the right equations, okay, is this one over here. So by knowing the value of the redshift, or by knowing the change in frequency, we can figure out the velocity, and there you go. There's the Hubbles Law. Well, there's Hubbles Law as we stated it. Another way to figure out the distance of a star is by using the idea of luminosity. So this is covered in the last video and the last ISP task, but there it is again. So we convert the distance if we know the luminosity or intensity. Pretty straightforward. So that's using the inverse square law. We've also mentioned parallax, and we've also mentioned the Hubbles Law method of figuring out the distance as well. Right, so let's get stuck straight into these questions. I think I've gone past them. That was last time. That's also last time. Also last time. Here we go. Okay, so the first question is a multiple choice question about the idea of CMBR. Oh, I've just realised I think I've missed out one of the explaining everything tasks. There's a high probability of me doing that. Yeah, there we go. Okay, so explain the importance of the Hubble's constant in determining the age of the universe and the ultimate fate of the universe. Okay, so remember, Hubble's constant, 1 over Hubble's constant is essentially the age of the universe, but you need to get the units right from the graph. Okay, so look carefully at the units, cancel them out to get down to seconds, and therefore allow you to figure out the time properly. It also says about the ultimate fate of the universe, include the role of dark matter in the fate of the universe. So remember, dark matter is matter that we cannot currently detect in any, well, we're now getting to grips with how we can actually detect it. One of the important things about it is it does affect the density of the universe, and the density affects the gravitational pull. So this is why Hubble's constant is so important, because if Hubble's constant is large, okay, then the velocity is also large. Okay, if Hubble's constant is small, then the velocity is small as well. So this could affect essentially the speed at which things are going. So Hubble's constant will affect directly the speed, and the speed will of course have an impact on the density. So in terms of if we had a dense universe, it's more likely that we'll have a big crunch. If we had a not so dense universe, everything's spread out, everything's moving really fast, the possibilities that the universe will go on forever in terms of its expansion. So if you had distance, let's get this. Okay, so if you had distance between galaxies, let's do a little symbol for galaxies. Okay, on that axis, and time on this axis, if we had the idea of a big crunch, it would come back on itself like that. If we had the idea of it going on forever, expanding forever, it would go on like that. Okay, so they're the two main ones that we talk about. Obviously, there's one where the density is just right, and it levels off. Okay, but they're the three main ones. One of the interesting ideas is we actually think it might be accelerating. Okay. So this ties in the idea of potentially dark energy or other ideas that cause it to accelerate. Okay, the three main ones they talk about, those two there, were the two ones that are most often asked about on these exams. The idea of the big crunch and the idea of it continue to accelerate. Oh, sorry, going on at a steady speed, expanding at a steady speed is the way I should state it. Sorry. Right. Okay. Questions. So the first one ties in the idea of CMBR. So I'm just trying to bring up my notes on this. There we go. Okay, and it talks about the idea that that CMBR is a remnant of the Big Bang. Okay, it appears to pervade the universe. It has a maximum wavelength in a microwave region. That's why it's CMBR, I called it, rather than CBR, which is what's written there. So this can be calculated to correspond to a temperature of about 2 Kelvin. This calculation is based on the assumption, okay, that the universe behaves, has a black body. Okay, so that's the only way we can really get from temperatures to wavelengths, by assuming something behaves like a black body. So that's C. All right. The value of Hubble's constant is thought to be 70,000 meters per second per megaparsec. Okay, give one reason why this value is uncertain. Okay, it's difficult to actually measure faraway objects, the distance to faraway objects. It's also difficult to measure the speed of objects that are so far away. It's difficult to do these measurements accurately. State how an estimate of the age of the universe can calculate from Hubble's constant. So it's the idea of a gradient of a V against D graph, which is Hubble's constant. And we do 1 over that to give us the age of the universe. That's the main sort of idea. You don't need to state this part. Oops, let's get the camera back to where it was. Okay, you don't need to state that part of it, but that's the main part of it. That part there. It's 1 over h, or 1 over h naught. Explaining the fate of the universe is associated with the Hubble's constant. This is what we were just talking about in terms of the explaining everything task. So the fate, remember, depends on the density of the universe. And there's a link between gravity and density. The more dense it is, the larger gravitational pull. Hubble's constant is changing due to these gravitational forces. That's why another reason why we can't pin down this value. So right, we've got a Hubble's graph. We've got a V against T recession velocity graph. Okay, so use a graph to determine the value of Hubble's constant in per second. Okay, so this is what I was saying about before. You need to cancel down these units. We've got 1 in light years, we've got 1 in kilometers per second. Okay, so it's a very straightforward question. First, take the gradient to figure out Hubble's constant, and then cancel through the units. So I'm not going to sit here and do that with you. The mark scheme shows it very, very well, so please do use the mark scheme. For those of you guys that are watching the video without the ISP directly in front of you, let me just show you the mark scheme. Okay, so this is the bit we're after over here. So it's just taking the gradient and the standard conversion after that. Pause the video if you need to look through that in a bit more detail. Thank you. Right, next part of that is what is the main source of uncertainty in the value of h? Well, it's d. Okay, it's distance. We know about that. Okay, we know about the main uncertainty is caused by distance. Okay, explain how the Hubble's constant can provide us with an estimate of the age of the universe. Okay, so it's 1 over the gradient of the graph. 1 over Hubble's constant is going to tell you an estimate of the age of the universe. Is that just a 1 mark question? I'm just going to check. Oh, it's 2 marks. Okay, so you need to get the unit into the correct. What they're asking for us to actually do is explain it. So yes, it is 1 over it, but why is 1 over it the actual value? Well, if you think about the gradient, the gradient of this graph is velocity over distance. Okay. Now, if you think of your equation as speed equals distance over time, just going all the way back to year 9, then time is going to be equal to distance over speed, or displacement over velocity, whatever you want to call it. Well, if you think the gradient is velocity over displacement, or velocity over distance, then 1 over t is going to be equal to v over d, or v over s. Okay, so whichever that is, so the s and the d are the same, displacement or distance in this situation. So the gradient is equal to 1 over. So that's proved that fact. That's all they're wanting for that explanation there. Alright. C. Ionized calcium is line spectra, which includes a spectral wavelength of 393 nanometers. The observed wavelength of the calcium line in the radiation from a distant galaxy is 469 nanometers. Okay, so we've got a change in frequency that's actually occurring there. Okay, so that change in frequency is due to a red shift. Okay, so we can see the value of that. It's 76 nanometers. Okay, so you need to use the equation of change in wavelength over wavelength, which will give you V over C. Okay, so change, so this was on the equation list, I showed it to you earlier, is equal to V over C. Okay, so you want the recession velocity, so V is equal to change in wavelength over wavelength times by C. I'm just going to whack that through my calculator to give you guys an answer. So it's 76 divided by 393. Remember, this all times 10 to the minus 9. So again, 76 times 10 to the minus 9 times 393, 10 to the minus 9. Oh no, it's a times, it should be divide. Okay. And then we need to multiply that by the speed of light. Okay, so you end up with a value of about 5.8 times 10 to the minus 7. So times 10 to the 7. 5.8 times 10 to the 7. Okay, so that's how fast it's going. Briefly explain how the value of the average mass energy density of the universe will determine whether this universe is open or closed. That's what we were talking about before in terms of these ideas over here. Closed universe, open universe. Okay, closed universe, open universe. So it's closed universe means there's going to be a high density above this idea of the critical density of the universe, which will allow it to be open. If you're above this critical density, it's going to be open. If you're below it, sorry, if you're above this critical density, you're going to be closed. If you're below it, you're going to be open. Okay, so if it's closed, you have a high density. The gravitational pull is big enough to make a big crunch happen. You could do the exact opposite argument for an open universe. Right, 19a. So, in spectral light received from galaxy X, we've got a change in wavelength again, so exactly the same calculation as the one we've just done for 18C, I think it is. Yeah, 18C. So I'm not going to go through that one again. It's the exact same calculation. But what you should get is 1.28 times 10 to the 7. Okay, so we've got another galaxy here. This time they're asking you to figure out the wavelength. So it's twice as far away. So remember, V is proportional to D, so you double your V this time. Okay, so you got 1.28 times 10 to the 7 for the first one. So therefore, you're going to use twice the velocity for the next one. So that's 2.56 times 10 to the 7. So you'd use the same equation. Okay, for B. This time, you know this. That's going to be a 2.56 times 10 to the 7. Let's have a look. Just double checking that's the right value. Yeah. You know this still. It's 3 times 10 to the 8. okay, they want to know at what wavelength would you expect the same line to be. Okay, so same line, so it's the same original wavelength. So that's 656 nanometers. So you'd figure out your change in wavelength. You'd figure out your change in wavelength, and then you'd add that to 656 nanometers. Okay, and that would give you your lambda, your new lambda. Okay, which is what they're actually after. Okay, should end up with a value of about 712 nanometers. Please show you're working for this question. They will only give you 2 marks if you don't show you're working for that type of question. Right, question 20 is talking about Hubble's constant again. Let's talk about measuring difficulty, measuring distances. One method of determining astronomical distance is to observe supernovae, since we can predict the luminosity of these exploding stars. State the type of reaction that produces energy in a star and allows it to radiate. That's nuclear fusion. That's pretty straightforward. Okay, determine how we can determine the distance of a star using the measurement of luminosity, of its intensity, and of light arriving at the Earth. Okay, so remember using the idea of F is equal to L 4/4 pi r squared. So that's a D, sorry, not R, and that, okay, that is written as I sometimes to the F, whichever way you want to do that. So let's put it again. That's the equation we're using. Oh, sorry, if you missed a bit from before, I just realised I zoomed in very far. I'll zoom out a bit more. If you missed a bit from before, feel free to pause the video to go to my working there. So that's the equation that we're using for BI. Okay, remember I is sometimes written as F and D is sometimes written as R, so don't get those confused. From the velocity of a distant star using the frequency of detected light. So we're going to determine distance. Okay, so if you're determining distance, remember you've got to figure out the redshift value, and you want to figure out the redshift value with you've got to figure out the frequency and compare that with the frequency from the lab. The change in frequency will therefore give you the velocity, and that's pretty straightforward. So essentially we're using this idea over here. Change in wavelength, change in frequency over frequency, which is approximately equal to V over C. Okay, so that's what we're using for the second part of it. That's the equation we're using for that. Pretty nice, straightforward questions for a couple of marks that we went through in explaining everything. Okay, complete the graph with line of best fit. So you're essentially looking for the middle of all those points there. And state what this graph shows about the velocity of galaxies in the universe. Further away the galaxy is, the greater its velocity. This is all relative to Earth, remember. So the further away the galaxy is from Earth, the faster it's actually going. The Hubble time, or 1/h0, gives an approximate age for the universe. Use the gradient to determine this time. Okay, so remember, take the gradient, do 1/h0, cancel out the units, straightforward. Again, it's in the mark scheme. I'll show that mark scheme for people that don't have the ISP in front of them right now. There we go. So remember to pause the video if you need to have a better look at that. Right. Question 21. So they want us to calculate the distance to the tree. Okay, we know that this is 10 meters from here to here. So we know the baseline. We know it's 84 degrees as part of this over here. So we want to figure out D. Okay, so essentially we've got a triangle as part of this. So here's our triangle. 5 meters and 84 degrees. Okay, they want to figure out D, the distance from the baseline to the tree, not the distance of P to the tree. So we want the opposite, and we have the adjacent, just going to be tan. It's TOA, so we want the opposite, so it's adjacent times what tan, so 5 tan 84. Very straightforward. State what astronomers use as their baseline in parallax measurements of nearby stars. They use two astronomical units. So because of the fact there's a sun and there's a planet, 1 AU is used from there to there. So the baseline is going to be all the way across. So that's 2 AU. Okay, just to make that clear. So the baseline is 2 AU. State why trigonometric parallax cannot be used to measure distance to stars over 100 light years away from Earth. Okay, so it's difficult to measure the small angles, and there's limited movement compared to the background then. Okay, so it's difficult to measure these small angles, and there's limited movement compared to the background. Okay, all quasars show large red shifts in the light received from them. So if there's a large red shift, that means they're going fast, and it means they're far away. They're the key things. Okay, so, and if it's a red shift, it means it's got to be going away from us. Okay, so first thing, large diameters, no. Low temperatures, no. Far away from Earth, well, yes, it does show that they're far away. Are moving towards us at very high speeds. Towards would be a blue shift, so D is the correct answer. They're far away from Earth. Remember, large red shift means that they're further away and going faster away from us. That's the idea. Well, that finishes ISP task 2. Next time, we're on to reviewing astrophysics. So thank you very much for watching, guys.